Okay, questions on the homework on U-substitution to find antiderivatives of very specific looking types of functions. Miss Wilkins. Number 4. This is 4-5. Number 4. With these antiderivatives, you kind of have to like see what your answer is going to look like. You got to see what could possibly cancel when you set your u equal to something. You can try out a couple, see if it works or not. Don't get discouraged. Like, let's say I choose u to be secant of 2x. Maybe I think that's the one. I take the derivative of both sides of this u. I get secant 2x tangent 2x. And I'm like, all right, that might work out. That might cancel with stuff. Times 2 dx. And then I solve for dx. I get 1 over 2 secant 2x tangent 2x. Now, I'm doing this wrong for a reason, so I hope you're not copying down. But if you are, it's okay. You would get u tangent 2x, and then I substitute this for dx. It becomes, I'll just move it over, whatever, that. And you're like, all right, tangent 2x goes away, tangent 2x goes away, but then I have this secant 2x, and I kind of like, do I replace it with u again? But then it's like just 1/2. That's probably not going to work, okay? Whenever you end up with u's and with x's, you did something wrong, or maybe you overthought things. In this situation, I overthought things. I should know that the antiderivative of just secant x, tangent x, is secant. This is the antiderivative of secant tangent. The derivative of secant is secant tangent. So thinking of that, I should be like, all right, well, I just got to worry about this 2x. So really, I just have to put a 1/2 in front, but maybe we'll just show you every single step. We'll set u is equal to 2x, du is equal to 2 dx, dx is equal to 1/2 du. So we would have secant u tan u, and this is the correct way to do this, times 1/2 du. Now, this is an easier function to take the antiderivative of. The antiderivative of secant tangent times 1/2 is just 1/2 secant of u plus a c. But of course, you will replace that u after you take the antiderivative with 1/2 secant 2x plus c. Okay? This is the key step. Don't forget to take the antiderivative of this simplified function. Do not substitute in after like stuff cancels. You substitute after you take the antiderivative. Okay, so this is the answer right here. And of course, with all of these, you can check your answers by taking the derivative, whether it's in your head or on paper. Take the derivative of your answer. Make sure you get this. And if you don't, you made a mistake. Other questions? 6. Let's do 6. All right, step 0 is always simplify. Step 1 is to set u equal to g of x, which is typically the inside of a composition of functions. After we take u is equal to g of x, we'll take the derivative, and that g prime will cancel with an existing g prime in this expression that we're given. So I see, Miss Coffee, a composition of functions, and I see that if I take the inside of that composition and take the derivative of it, I'm going to get rid of something else. What would be the inside of the composition? Does that help? No, doesn't. Mr. Glubke, what is it? Sine x, exactly. It's going to be sine x. Why is it sine x? Because the derivative of sine is cosine. This cosine will go away when I solve for dx when I take the derivative of this. So this is the inside of your composition. This du would be this. Solve for dx. Substitute in u, substitute for dx. So I get cosine x, that doesn't change. This would be u squared, that's the composition. Then I replace dx with 1 over cos x du. Well, there is that canceling that I need to get rid of x's and just have u's, leaving me with a simpler expression that I can take the antiderivative of, 1 over u squared. Now, here, you will probably be best if you rewrite this as u to the negative second, and then you will apply the power rule. So add 1 to the exponent, multiply by the reciprocal. That is your antiderivative, and of course, the last step would be to substitute back in what u is equal to, and maybe make it look a little nicer. Negative 1 over sine x plus c. Okay. Other questions? Ms. Griswold. 20. All right, I see a composition. The denominator has that 1 plus x to the fourth. I see that the numerator, that x cubed, is going to be the derivative of that x to the fourth. So I'm immediately saying, all right, u has got to be that inside of that composition. And when I take the derivative, get 4x cubed dx and solve for dx, I'll be able to cancel that x cubed. Now go ahead and substitute in u, substitute for dx. You should have things cancel if all is right in the world, and it is. And we get 1/4 u to the negative second du. That's not it, though. You have to take the antiderivative of this, so make sure you do that. That's going to be u to the negative first times negative 1/4 plus c, which is negative 1 over 4, 1 plus x to the fourth plus c. All right, Suusu, number 26. So a lot of these problems towards the end, the book did this on purpose. They were trying to trick you to use U-substitution when, in reality, you did not have to for like the last 5 problems. This is one of those situations where U-substitution will not work, even though this looks complicated and you think, oh, I have to use U-substitution when things are complicated. Not the case. Step 0 is always try to simplify, always attempt to simplify. For this one, I could simplify the 1 over 3x squared to not be a composition anymore. This will just be 1 over 9x squared. Or that's just x squared plus 1/9 x to the negative second. I can take the antiderivative of both of those individually. You can split them up into 2 pieces. There's no U-substitution needed. It's just going to be 1/3 x cubed plus Negative 1/9 x to the negative first plus AC. Yes?
So that's the kind of problem you're talking about on the video where U-substitution just won't work at all.
U-substitution will not work at all. It'll just make things more messy, more complicated. It will not help us.
Are those for all where you just add?
Not necessarily, but typically. If you see stuff that's being added, like 30, like 32, U-substitution would just make that more complicated. Like 34 even, 34, you just distribute the 2 pi y to the 8th and to the y to the 3/2, and actually that's an easy antiderivative to take. It's just 2 pieces. They put these in there just to screw you up. If you looked at the odds too, you would have seen what they did. They did not use U-substitution for any of these. They just distributed and took the antiderivative. Okay, Mr. Griswold? What can you do? What do you mean?
Like for the, how do you take the antiderivative, like t over the root t?
So you would simplify this by dividing the root t into both of these terms and just making it 2 separate terms. So this would be root t plus 2t to the 3/2. And then you can take the antiderivative of that. I'll show you. So this one is another step 0 problem. Divide both of these by root t. This becomes the antiderivative of root t, because this is t to the 2/2 divided by t to the 1/2. That's t to the 1/2. So I'll just keep it as t to the 1/2. Plus, this is t to the 4/2 divided by root t, or t to the 1/2. That's 2t to the 3/2. You can take the antiderivative of this. This will be add 1 t to the 3/2 multiplied by the reciprocal, 2/3. Add 1 t to the 5/2 multiplied by the reciprocal, it's 2/5 times 2, that's 4/5 plus AC. Okay, anything else? Number 52. All right, I see a composition. I see one piece being a derivative of another piece. Both of those should point me towards what I should select for U. What should I select for U? Tangent. This is tangent to the 1/2. The derivative of tangent is secant squared. So when I set U equal to tan x, when I take the derivative of this, I get du is equal to secant squared x dx. I see when I solve for dx, that secant squared is going to cancel with that other secant squared. So this would be u to the 1/2 secant squared x times 1 over secant squared x du, cancel, cancel. Have an easier function, easier expression that I can take the antiderivative of. Add 1, multiply by the reciprocal, add a c, substitute back into u. Okay. Anything else before we take our quiz? Sure, 54. 54 is just like number 4. The secret is in the composition. The composition is in the denominator. It's cosine of x being cubed. So think of the denominator being cosine of x quantity cubed. That's your f of g, or f prime of g. So you'd set u equal to that cosine, go from there, and you'd figure it out. All right. Anything else? The A-dayers will only have an hour and 15 minutes. So the A-dayers are probably going to get to most of the video for the lesson, but then they'll have to watch it. Sorry, the B-dayers. The B-dayers. B-dayers will be able to watch most of the video for the lesson, but then they'll have to watch the rest of it at home. Okay? Anything else before we start the quiz? Okay, let's pass up our homework. I will collect the homework and put it in the box. I will then give you the quiz. The quiz is no calculator. There are no corrections for the quiz. So just do the quiz as you see it. When everybody's done with the quiz, we will start with the lesson, like normal. It says round to 3 decimal places, but that doesn't make sense because there's no calculator allowed. So you shouldn't have to round anything anywhere. You do not have to use U-substitution for all the problems. That in the box we gotta look at. Turn this into the box when you're done looking at it. All right, we should be finishing up in a couple of minutes. And then we have our notes. I don't know. I haven't done it yet. I don't know. I think it does, yeah.
No.
Yeah, pretty sure it does. Okay. Second lesson is on areas under a curve using U-substitution. So it's just an extra element to last class. But then we also will talk about the antiderivatives of e to the x and log x, which will kind of be it in terms of antiderivative techniques that we have to learn. If you're taking the BC test, there's a couple other techniques you have to learn. Okay. So first, let's remember that if I have this, the answer is just an antiderivative because there's no numbers. It's just some f of x plus c. But if I have an integral with values from like a to b, this is no longer just an antiderivative. This is the area under a curve. But we use the same notation because area under a curve is just the same as the change in the antiderivative. Okay? So if you have the area from a to b under f prime, you just find f, and you find the change in f from b to a, from a to b. Okay, so let's look at this. Let's find the area under this function from 0 to 2. Okay? Well, first I have to know that I have to take the antiderivative of this. And if I look at it, I can't take the antiderivative of it just as I see it because it's a difficult function, something that I have to use U-substitution for. So let's do that. I'll set u equal to typically the inside of the composition. What should it be in this case? X squared plus 2. I'll then take the derivative of both sides. I'll then solve for dx. Okay, and then I'll go ahead and substitute in u. I'll substitute 4 dx. And I get this. And we see that the x's will cancel. That's good. And I end up one more step having this. Well, I'm missing stuff, right? What am I missing in these two integrals? The a and the b, right? Well, here's the tricky part. And it's kind of tricky, but it also isn't, depending on how you think about it. Both of these are x values. This is your kind of left and right boundaries. And this dx tells us that those are x values, because it's like an instantaneous change in x. It's like a very, very skinny width of one of these like rectangles. So those are x's. Well, once I switch from dx to du, these no longer are going to be x's. This is no longer 0 and 2 necessarily. Could be. But in this case, I need u's. What would be the u's that I use there? That's exactly right, Mr. Barron. You need to use your connection between x's and u's, and you need to plug in 0 into that x squared plus 2 to give us that this bottom u is 2. And then when x is 2, you plug it into x squared plus 2. That gives you a u of 6. So it turns out the boundaries change because the variables change. That kind of makes sense if you think about it. We're no longer in the realm of just like an x-axis. This is now like a different axis, a u-axis. This is an instantaneous change in u. Okay, so now that I have the correct u's, the correct boundaries, I can take the antiderivative. I get u to the 4th times 1/4, so that's 1/8. And I'd find this change from 2 to 6. And of course, the antiderivative, you remember, is 1/8 u to the 4th plus c. But we also remember that if this c is just a value, a consistent c, it will cancel when we find a change in it. It turns out it doesn't matter. Okay, so we can do this. But what if I always like to put my answers back in terms of x, and I plug in the x squared plus 2 back in for u? What else would I have to do? What if I just said this is 1/8 x squared plus 2 to the 4th plus a c that goes away? What's that? Yeah, it actually goes back to 0 to 2. So you see, we can either change them and keep them changed and plug these values in for u, or we can really just keep them and just make sure we go back to x's. There's really 2 ways to do this and 2 ways to get the answer. We can either have the u's changed and use 1/8 6 to the 4th plus 1/8 2 to the 4th. Or, notice if I plug in x squared plus 2, I plug in 2, I'm going to get 1/8 6 to the 4th. That's not a plus. Come on, guys, catch me on that stuff. Minus 1/8 6 to the 4th minus, this would also be 1/8 2 to the 4th. So you get the same answer. It's just either using u's or using x's. It's important to see that they're both the same, that it's okay to keep with u's, or it's okay to go back to x's. Well, most of you are like, well, why do I even bother with U's? I'll just keep X's. I'll make sure I plug in back an X. And I'm not even going to worry about changing things. Well, because you'll have questions that'll force you to change things. Like this one. Okay, so let's write this question down. And let's see what they're going to be looking for. So they're saying, what would the equivalent definite integral using f of u be instead of f of 2x? So really, they're looking for this as an answer. And they want you to figure out what this number is, what this number is, and what that number is. See if you can do it. Check with a neighbor. See if you got it. See if you're lost. See most of you doing the right things. I start by setting u equal to 2x, and I know du is equal to 2 dx. That means dx is equal to 1/2 du. So I'll go ahead and substitute in. And I have that 1/2 there. But now that I have du, I need u's. Well, here's the relationship between x's and u's. These are x's. To get the u's, we will substitute in 4, multiply it by 2. This is 8. Substitute in 9, multiply it by 2. That is 18. And I got 1/2 f of u du is equal to 6. That's not going to change. So we all know that this is going to be 8. This is going to be 18. But in reality, they only have the 1/2 here. So you have to kind of bake it into this number. You can factor that out. You know, you can pull out a constant from any area that you want to find, and then I can multiply both sides by 2, and this becomes a 12. Okay? So that's why you'd have to know how to change, you know, from x's to u's. If you have dx, you need x's. If you have du, an instantaneous change of u, your boundaries on your u-axis, your boundaries are on the u-axis, so you need u's. Okay? So that's the answer to that. Let's go ahead and just do one for practice. Let's make this that. You know, you kind of had something like this on your quiz today. I didn't think it would have been a problem because you just would all have gone back to x's. So let's see if you could do something like this. No, you're just trying to find the answer. I don't care how you do it. I don't care if you just stick with x's and you make sure you go back to x's and plug those back into x's, or if you change things to u's and you use u's. I'll show you both ways on the board. Look at that. Okay, it should get 0, only because the sine of pi is 0 and the sine of 0 is 0, so you don't have to worry about that. You could have gone back to x's. If you had u's, you would use pi and 0. If you had x's, you would use pi over 2 and 0. But it should make sense that when you plug this in and this in and plug that in and that in, you get the same values, you get the same thing. Okay? So, but that was just good practice. Let's move on. Talk about the derivatives of e to the x, and then we'll talk about the antiderivatives of e to the x. So who remembers the derivative of e to the x? E to the x. What if we had e to the x squared? Exactly, chain rule. Good, everybody remembers that. So the chain rule applies with e to a power, be e to the power times the derivative of the power. That's the composition of functions. This is an f of g. We could have a g and an exponent. So this is a situation where f of g is e to a power. Okay? So good. Well, let's go backwards. Guess what the antiderivative of e to the x is? E to the x. It works both ways, plus c. Okay, but what we will find often is that we will have U-substitution with e. So typically what you'll see is you'll have a g of x, g prime of x, e to the g of x, dx. So here is your composition of functions. Here's your g prime times f prime of g of x. This g of x is inside the composition. So if you were to undo this and to take the antiderivative of this, you would set u equal to g of x which is typically going to be the inside of your composition, which is your power. Okay, so whenever you see e to a power, typically, if you want to take the antiderivative, you'll set u equal to that power. Then when you take the derivative, you'll get g prime of x dx. When you solve for dx, you'll be able to get rid of that g prime. E to the g. Okay, so let's do examples of finding antiderivatives of e to a power. All these examples will use U-substitution. Typically, you won't see things where you can simplify, maybe, but here are a couple. So for these, the g is the power. When you take the derivative, you'll be able to get rid of g prime. In this case, there's really no g prime to get rid of, so you just have to worry about the constant. Then the antiderivative of this easier thing is just what it is. But you can go ahead and replace the u with that 3x plus 1. Okay. Do the other one if you haven't done so. It's 5x e to the negative x squared. Here, the composition is in the e. It's e to a power. That's an f of g. So you'd set u equal to that g, which is the power. And we'll notice as long as this problem is set up correctly, we will have stuff that will cancel, which is what we're looking for, giving us an easier function. So we'll be able to take the antiderivative of. Here, the x's cancel, leaving me with just negative 5 halves e to the u. The antiderivative would be negative 5 halves e to the u plus c, which is negative 5 halves e to the negative x squared plus c. All right, let's see if we can do at least one more. Yes?
How come you don't take the antiderivative?
I did. The antiderivative of e to the u is e to the u. It's only this easy for e's. All of the other ones we've done, yes, we've used the power rule. We've done we made sure we didn't skip the step of taking the antiderivative. Just, I'm not skipping the step. This is legitimately the antiderivative of that. That's the antiderivative of that. Okay? Both of these are good to do, actually, so we might as well do them. And then we need to move on to 1 over x. As long as the problem is set up right and you're doing everything correctly, you should see stuff cancel. Make sure you're taking your derivatives correctly. I know that we're now doing derivatives and antiderivatives all in the same problem, so we get the two, mixed up in our heads. So be very careful. Derivative of x to the negative 1 is negative 1x to the negative second, or negative 1 over x squared. You solve for dx, you get x squared, negative x squared du. So this becomes e to the u over x squared times negative x squared du. That cancels. Get the antiderivative of negative e to the u du, which is negative e to the u plus c. So negative e to the 1 over x plus c. Okay, the final one, this 1 over e to the x. Key is to rewrite it as e to the negative x. Once you do that, you can set u equal to the negative x, or you could pretty much just figure out that this antiderivative is going to be what? Negative e to the negative x. Once you do that, you're good. But if you don't rewrite it, you're going to get stuck. You're not going to know what to do. Okay, brings us to this. What is that? Go for that. Go do that. What is the antiderivative of 1 over x? What's our first step? Step 0. What do we do? Try to simplify, right? So you go and you say, okay, this is the same as the antiderivative of x to the negative first. And you're like, all right, I'm going to use the power rule. I've been doing it for every single antiderivative that I've taken. I'll do it for this one as well. I use the power rule, and I add 1, and I multiply by the reciprocal, and I get that. Yes. This is This does not exist. This does not work. The power rule does not work for this. Now, what's funny is that you would think it's like, I'm sure I've done that before. I'm sure I've seen it because we've taken so many antiderivatives so far in this semester. You would have thought I saw an x to the negative first somewhere. You didn't, for a good reason, because you didn't know how to take the antiderivative. Now, don't forget that the power rule does work for 1 over x squared. Don't forget that this is just the antiderivative of x to the negative second, and this is easy. You can just x to the negative first times negative 1, so this works. It's just when it's 1 over x, the power rule doesn't work. So, what is it? Well, let's find out. What was the derivative of log x? One over x. So guess what the antiderivative of 1 over x is? Log x. It's a little more complicated than that. So this is, wait, hold on. Nope, not here. Yes, here. Okay. Let's think about log x and 1 over x. So when I took the derivative of the logarithmic function, here was the logarithmic function. It looks like this. Something like that. Log of 1 is 0. Log of e was 1. We kind of could look at it there. And of course, logs grow very, very slowly the further and further away you get. But it trends towards infinity. Okay? So when we looked at the slopes of the tangents of log, so the derivatives are positive, they remain positive, less positive, less positive, less positive, less positive. That's how we got the whole 1 over x picture. Positive values, less positive, less positive, less positive, less positive. But notice, this is only for the right side of 1 over x. This is really true, this is very true, but it's only when x is greater than 0. Which means that the right side, this is true only for x is greater than 0. The antiderivative of 1 over x is log of x when x is greater than 0. But when we're talking about 1 over x, and we're starting with 1 over x is actually defined everywhere but at x equals 0. So there's 1 over x over there. So it turns out this is not the correct antiderivative, we would say, because it's not including the stuff to the left of x equals 0 that log can't, have. So the way we get around that is we use the absolute. Turns out the derivative of log of absolute x would look like this. It's just the same thing on both sides. And you can see these tangents are negative, more negative, more negative, more negative. Here are negative values, more negative, more negative, more negative. So this is actually the same thing, but these are for all x's except for 0. So for this guy, the actual antiderivative of 1 over x dx, we would say, is the log of absolute x plus c. And that's because we are defining x as everything that it can be plugged into 1 over x for. So if I want to find the area under 1 over x from 0 to, or from -3 to -1, I could find that, but if I use log of x, I can't plug in the log of -3, but I can plug in the log of 3. That I can find. Okay, just deals with the whole symmetry of things. Okay, now remember the chain rule works with logs as well. So if I have the derivative of log x, 3x cubed plus 2, that would be 1 over the function times the derivative of the function. Okay, and that's going to help us, just knowing that fact, going backwards. And we'll go back to these. You don't have to write this down. We'll just start taking some antiderivatives of stuff with x to the first power. Okay, so if you have 1 over x, turns out your log absolute x, not the power rule. Let's look at these two. These are simple antiderivatives where we'd end up with an x to the negative first power. Go ahead and give them a shot. You can just rewrite it as 3/5 times 1 over x, or 3/5 times x to the negative first. The power rule doesn't work with x to the negative first, so you have to remember, oh yeah, it's 3/5 log absolute x. Okay, try the second one. The x squared plus 1 over x. This is one of those, hey, step 0, simplify first. But after we simplify, we'll realize that we'll have to use our newly acquired knowledge of the antiderivative of 1 over x. Simplify by dividing both terms by x. I get x plus 1 over x. I can take the antiderivative of x to the first. That's 1/2 x squared. I can't take the antiderivative of x to the negative first using the power rule, but I can remember that it's the log of absolute x. Okay? We'll come back. U-substitution with these. If we notice that we have stuff in the denominator and stuff in the numerator, and the numerator is the derivative of the denominator, we can use U-substitution. This is how it would look like. It'd be the antiderivative of g prime of x over g of x. Could be f of g of x, typically just g of x. It's g of x to the first power. That's what it is. You would set u equal to the denominator. You take the derivative. When you solve for dx, that would be able to get rid of the numerator. That's that g prime. You'd end up with g prime of x over u times 1 over g prime of x du. Goes away, goes away. 1 over u du log absolute g of x plus c. Okay, that's the whole U-substitution process where you see a numerator being a derivative of a denominator. So take this one. This is a good first example. The antiderivative of x over x squared plus 1. So here, with e to the x or e to something, we set u equal to that power. Here, with logs, we'll end up setting u equal to the denominator. That is going to be the inside of the composition. You just can't see the composition because this is like g of x to the first power. Set u equal to the denominator. Should cancel with the numerator. I get x over u, 1 over 2x du. X goes away. I'll get 1/2 times 1 over u du, which gives you 1/2 log absolute u, which in this case is x squared plus 1 plus a c. What have we done? 26, 21? 26? Good. More problems to do. Like these two. Here I don't see the derivative of the denominator being in the numerator. Well, it kind of is, because the derivative of 4x is just 4. The derivative of negative x is negative 1. So let's see if we can figure out these. For both of them, you're setting the u equal to the denominator, just like you did in the previous one. Only the difference is they'll just produce a constant that will help you figure these out. This is 1/4. 1 over u du. This is 1/4 log absolute u. That's the antiderivative. This guy would be negative 1 times 1 over u du. Negative log 5 minus x plus a c. Okay, there's a couple more that we could do. It's the same deal. This one's good. Do this one. Find the antiderivative of 1 over x log x. This is not as simple as setting u equal to the denominator. This is a little more thought involved. I need to cancel some of these x's. What should I set u equal to? Let's see, if I set u equal to 1 over x, the derivative du would be equal to negative 1 over x squared. That's not going to get rid of log. That's not what we wanted. Maybe just ln, actually. Because du is 1 over x, dx would equal x du. That's going to get rid of that x. Now watch this. This is going to be fun. X cancels. Okay. I got the antiderivative of 1 over u. What's the antiderivative of 1 over u? Ln absolute u. What is u again? Ln of x. So this is ln of the absolute of ln x. Whee! All right, and then the key rule is, just because you know this whole ln thing doesn't mean forget about the power rule. The antiderivative of 1 over x squared is not ln of x squared. Use the power rule, just like you've been doing. Okay? Same with 1 over e to the x. The antiderivative is not ln of e to the x.